Hello guys, today we start adding some ambient into our ecosystem. And the first one I found like the most necessary and pretty much easy to implement is to make the swarm or fireflies with the help of Niagara. Well, this tutorial is not pretty much simple, but it's not too advanced. And let's start. So, first of all, the material for our fireflies or swarm. You can go with any kind you want. You can even go with the mesh instead of simple sprites, but I'm here to show you the flow, the idea, so you can implement and adjust it yourself. Well, the setup is pretty much simple. Translucent, shading model unlit. Next, particle color into the emissive color, particle alpha with the radial gradient exponential to make some sort of round shape. Also, I have noise here with this setup and the multiplier with particle random value and time with the sine function. So, as you can see from the preview, it's simulating some sort of flickering for fireflies that are actually flickering. It's their natural behavior. So, simple time, particle random value returns the values from 0 to 1, then we clamp it with the minimum of 0.5, so it won't be fully transparent. I'm sorry guys, that's my kid. One moment please. So here we are back again. Also sine here just to make it flicker like 0.5, 0.5, some sort of wave. And that's all for the material. Next, I guess we'll start with our blueprints. We need two blueprints. One for the attractor. It's the simple representation. As you can see, parent class is default actor. And here I have sphere with some custom attributes and the element that actually makes some emissive. It looks like this, and it's just for the sake of the demo. So when the attractor is active, it starts emitting some light, and it'll change glow during this activation period. So, then begin play. I have a function called each 0.2 second. It's called check time. And here I'm trying to get the current time from the weather system, because the outdoor lights or our attractor, as the swarm of fireflies, should appear on the particular time. So please follow my tutorial about the weather system. The link I'll leave in the comments or write down the video. So just quick show what it does. Here's the simple function get weather system, and by this I have the reference to my weather system. Then I use current time, and as you can see, I try to receive the value from the curve. And as you can see, this curve is vector, this one, and on different axes I have different behavior for different actors. Like the x-axis is for the period where outdoor light or our particle attractor becomes active. The y-axis is for our fireflies or our swarm, and it tells when our swarm should appear, at which particular hour. And I just check whether the value equals 1. So if it's so, I start emitting my light with the glow of 6 and set this actor as active. If it's false, it's the opposite one. So it's imitating some sort of the outdoor light. Let's talk about the vector curve. It's this particular asset. I use vector curve, so it's called night ambient, to control like Attractor and the swarm together is the full feature. So different axes, different behavior for different actors. As you can see, the x-axis has this layout, where the values are 1, it means our attractor is active. Where it's 0, it means it's not active. And as you can see, the bounds are from 0 to 24, so it's the full day. I'm sorry, one more time. Now we're back again, one more time, and the y-axis is for the time where the swarm should appear. Also, bounds are from 0 to 24. So, as you can see from this preview, our attractor, or our outdoor light, has some period, just for the sake of the demo, where it switched on and off, and then from like 24 AM till 5 o'clock in the morning, or 4, I'm sorry, it's active. Also, our swarm appears earlier and lasts also longer than our attractor switched off at this particular period. Now back again to our outdoor light. The reason why we use here this boolean is because our outdoor light will be the reference as the attractor for our fireflies actor, and we will check this status to actually tell the Niagara particle system where our attractor position is. Now I guess we can go to our blueprint of fireflies, or our swarm. That's actually the whole setup. Basically what we need here is the box collision, as for the collision, it's set to be query only, world dynamic, and it's ignore everything but overlaps our pond. We need these bounds to tell our particles where it should switch off or switch on, so it won't be emitting any particles where we are outside of this bound. And here Niagara system. Actually, as you can see, we have Niagara emitter of fireflies, and we also have Niagara system of our fireflies. So please provide this reference to our system. And you can also see that we have the same curve vector variable with the same setup. This one. Now, let's talk about other variables. Also, as you can see, parent class is simple actor. We have Attractor. It's the reference to our outdoor light. Make sure it's set to be visible so we can provide the link to our reference through the level on our scene. This one. Next, attraction force, attraction radius, spawn radius, activation zone, and high offset. So, spawn radius, simple, the radius where our particles should be spawning. Activation zone is the bounds of our collision box, so overlapping it we will activate the spawning for our particles. High offset is to tell where our Niagara system should appear on the z-axis. And attraction force and radius, simple attributes to control how our system should perform. So, at this point, I think we should talk about the Niagara emitter and then about this setup. So, Niagara emitter fireflies. As you can see, its target is to be CPU, because actually GPU particles could not have the light renderer inside, and we don't need, I don't need a lot of particles emitted at one time to simulate the real-life fireflies behavior. But you can switch off the light renderer and go with GPU simulation. And for this you need to set the fixed bounds for your system. Make it large, so it won't have any visual artifacts when the bounds of the particles are out of sight, and it won't be popping up. Next, emitter state. Loop duration is infinite, loop behavior is once. Life cycle mode is self. The spawn rate here, for my sake, is low, and I found it better have the low spawn rate to simulate the real-life behavior of the fireflies appearing when the day comes to night. As for initialized particle, I have random values for the lifetime. Color mode is direct set, and here is my color. Also, it has uniform sprite size set by 2. I also have cylinder location and cylinder height is like that bounds under which our particles should not be spawning. Here is the default setup, but as you can see, for the cylinder radius, I have the custom attribute. It's the user exposed variable. So for the cylinder radius, I use spawn radius. You just need to press on the cross and look for float. Make the same setup here. Attraction force, attraction radius, attractor position, avoid direction, avoid position, kill radius and spawn radius. So, if you talk about the avoid position and direction, is for like if the person comes inside the swarm should avoid it and it starts fleeing. So we need these two vectors to tell the direction and the position of our attractor. In my case, it's my person, my character, but you can use it as the lighter in the hand of your character. The kill radius we use, like as you can see, kill particles in volume, so our particles won't be existing outside this box. Everything else, I think it's obvious. So, once you've added, all you need is to expand the triangle and add your user exposed attribute inside the proper field. So, also, coordinate space for the cylinder location is set to be world. And actually that's all for our location. Next, here you can see I've added a void cone, and this one module helps us to make our particles flee. I have random range float, so each particle will be affected differently to simulate the more realistic behavior. Also, I have apply constraints, and as you can see, this one will help us to avoid our particles flying on the z-axis too high. So without it, our particles would flee in all directions. With this setup, our particles will flee mostly on the x and y axis. As for the cone, I use radial fall-off, and as you can see, cone apex and cone axis, I have avoid position and I avoid direction. Position is for telling where our attractor or our avoid actor is located, and direction, it's like the x-axis of our avoid actor. So where are we putting our cone, there our particles would start fleeing. So think of as a lighter in the hands of your character. Coordinate space is set to world, and fall-off angles are set to 180 to cover like the whole area in front and on the front and back sides of your character. So the full area cover. Fall of radius set to 150 units, making it larger won't be suitable for the character. So if you use larger or bigger values, particles will start fleeing earlier, not when you actually step inside the swarm. The next one is my custom module script. This one, we'll talk about it later. Here, kernel noise. Simple setup. The higher value of noise strength is, the more realistic behavior of the swarm you will receive. So, with low values, your particles will fly like they won't change their direction on the all axis quickly. So lower values make them behave as a dust, not as the flying thing. So having larger values make it more chaotic. Next, collision module, and as you can see, we have the CPU simulated, so it's CPU collision type. It's set to be ray traced. The particle radius scale is set to 5, just to ensure that the small particles, the size of our small particles won't be the issue for having artifacts. Bounce and friction can be set as you want. For the bounce, 0.6 is quite good, and for the friction I use 0, so because it's swarm, it should not be stopped by the surface. I also disabled rest state because I don't need it to be stopped by the volume. So when the swarm like beats at the wall, it starts searching for new direction to flee. Next, kill particles in volume. I use sphere kill shape, and sphere radius is my custom attribute kill radius. Also, as you can see, it has inverted volume, so everything that comes out of this volume will be killed. Sprite renderer. You can go with any material that you want. As for the demo, I used the stars, not this Firefly, but it was to just make it look more clear, to show you the technology. The basic setup here. As for the light renderer, I use color add with this value, so it's similar to this yellow color, but not too high. And I guess that's it. Now, when we're done here, we can go back to our Firefly's blueprint and make some adjustments with our user exposed attributes. This one. So, on the construction script, first of all, we need to set up our spawn radius. So please make sure that the variable names and the variable types are proper one. So if it's float or if it's vector, you use the proper float or vector nodes. As you can see, each node where I set up the radius, my value is divided by 2, because if we don't use it, our radius will be like the diameter. And to make sure it's like the properly world units aligned, we need to divide it by 2 for our spawn radius, for our kill radius, and attraction radius. Also, I have set box extend here with this particular setup. The reason why we don't use division by 2 is because set box extend by default, this one are like divided by 2 by default, and that axis is set to 2000 units because I don't think that we need to make it like very big. Also, I use set relative location for the Niagara, this one, to make the offset on the z-axis to tell where our particles should appear. So, now let's talk about our logic. On the event begin play, I check whether my player character, it's my custom function. You can go with get player character and check whether it's overlapping our box by default. If it's so assume that you start your game and you are overlapping right now. If you don't do this, your overlap event won't trigger. So you will need to step outside and then step inside the box to trigger the activation. So if it's so, we start force check time. It's this custom event, and I have it to start the new event, which is called check time, every 0.2 seconds. And what it does, it checks if we have the proper time to start our fireflies or our swarm emitting. So it gets the current time from weather system, then on the y-axis from our night ambient curve we check if our value is equal 1. If it's so, we activate our emitter, our system. Also by default our system should be set to not auto activated, and if it's false we just need to deactivate our particle system. Then we are telling our system our avoid position and avoid direction. For the avoid position I use actual location of my player character, and for the avoid direction I use the camera forward vector of my character. Then I check whether the attractor is valid. So if we don't have any attractor, our particles will flee or only. Well, if we don't have any attractor, our particles, in case our attractor is the light, so if the light is active, all like insects should fly to the light. It's the normal behavior. If you don't have this attractor, they just will be flying over the specific area. But if it's active, it should start accumulating near the light. So if it's valid, we also check if it's active. Remember this particular boolean. So if it's active, we start setting our attraction force. Also our attractor position, and this is the position of our attractor, our outdoor light. And if it's not active, we need to deactivate our attraction force, so our particles or our swarm will not fly onto the light. So that's our check time function, and also our overlap events. So when we start overlapping our box, we check whether it's our player character. So only our character will trigger the particles emitted. If it's so, we do the same. We start checking the time. And when we end overlap, we clear and validate our timer, this one, and we need to deactivate our system. So when we step outside the box, our particles will disappear. Now this also is done, and we need to just talk about the Niagara module script. This particular script actually works as the point attractor with the repulsion. So let's talk about this. So, Niagara module script. To create one, all you need is to press right mouse button, select FX and go with Niagara module script. That's it. So, this is custom logic that we need to make because by default we don't have any attraction force with the repulsion. Category is set to be custom. Mixed flags are default one. Also, it is exposed to the library. So, as you can see, I can search it here. Next, by default we have the map get without any attributes. And we need the following: default particles position, and all other are our dynamic inputs. So what do we do here? We subtract the attractor position from the attractor position, the position of each particle. Then we use direction and length to actually see at which direction our particle should be attracted and should be repulsed. Then we use this vector multiplied by the attraction force and the same but with the repulsion force, but here we use negate. As you can see, it returns the opposite value. And then we use simple lerp just to check at which particular position we should attract our particle and at which we should make it flee. That all goes to the default particle velocity. As for the alpha, I use remap range of the attraction radius minimum and attraction radius maximum. It also can be called like inner and outer radius. So we have some sort of circle where our particles should behave as you saw from the demo. The minimum radius sets the minimum distance between our attractor and the particles. The maximum is fall off for, or not fall off, but the max distance at which particles should be attracted and at which they should be repulsed. I use remap range and use the length of this subtraction to check whether it's higher than minimum and lower than maximum, to receive some sort of alpha between 0 and 1. Then I clamp these values and use 1 minus just to invert the behavior, and it's our alpha. Everything is simple. So, to add attribute, each particular parameter here has its own way where it should be called and written. So, for the particles position, we just need to select particle attributes and here look for position. That's it. For the dynamic inputs, we should go for the module inputs and here use float or vector. As you can see, it's a new attribute. We can rename it like this. And we need to drag and drop it into the map get. So that's it. As for the map set, as you can see, we have particles velocity. We also do let's see what we can have here. Position, velocity, lifetime, for instance. Then we just need to drag and drop it here. So it works. So simple. Well, once also, one moment please, by default, for instance, if we check for the subtract and for the remap, also I think for lerp, maybe, no, not this one, but this and other nodes, as you can see, have Niagara numeric. So to change the inputs and outputs, you just need to press right mouse button and convert numeric to particular attribute that you need. So like this, go to float, and you will receive the same layout. Also, by default, this one will return Niagara numeric, and we need to have direction and length. You can make it like this, or you can, by default, select it to be the vector 2D, for instance. So, as you can see, right now, if we drag and drop, or pull, not drag and drop, pull a wire, we'll see that this type is vector 2D, not Niagara numeric. So, please be careful with this particular types. Some of them use dynamic type and they are automatically converted, but for particularly this one, you need to make it by hand. So, when our module script is done, we can go to our emitter and add it right here under the particle update. It will have the prefix NMS and attraction, just as we called our module script. And here you can see I have this setup. So by default it will look differently. Like this, and we need to make it look like this. Well, I found it comfortable for me to control my particle system
only by setting from the blueprints the attraction force and attraction radius. All other elements, I use them with the default these two attributes and use coefficients like multipliers to adjust the behavior. So as you can see, attraction radius minimum is our attraction radius, and for the maximum I use simple multiply float. As for A, I go with the attraction radius, this one. As for B, simple value. It's not such a big deal to like make every attribute exposed. Find the perfect middle, like find the perfect balance for this. So for the attraction position, I have subtract vector. Here I can make some sort of offset where my attracted particles should be located. Like if we talk about the lighter, they should be a little bit lower than the light bulb. As for the repulsion force, I also use multiply float, and for A I go with attraction force, and for B it's simple multiplier. You need to play around with these values to see how it will work. So by default, setting higher attraction radius maximum will lead that your particles, the distance between the epicenter of your attractor and the ends of the sphere will extend and it will look more natural. The lower the value is, the more like uniform sphere shape you will receive. Also repulsion force, the higher it is, the particles will flee from the epicenter with the more speed. So search for your balance. As you can see from this setup, it's how actually my particles from the demo looks and works. So that's all for this particular episode, or actually the last things left is how to set up it on the scene. So place your Firefly's blueprint onto the scene, make adjustments. Next, add your attractor. Here I have it. Make it with the proper location, attributes, and provide it as a reference to our Fireflies. Well, I hope you like what you see. Please leave your comments, your feedback. Subscribe if you like my videos. I also have the Discord server where I can leave my feedback and help you if I can. So I guess we'll see you next time, and thank you for watching.